Hey everybody, limits in differential calculus, day number 4, part 2. We're going to do a little bit more with the second derivative, as well as do some curve sketching and bring together the attributes of f, f prime, and f double prime. So let's get started. Okay, a review style question, going back to part 1. This question is asking for the intervals in which f is increasing and decreasing. So for an increasing portion of f, f prime will be greater than 0. Decreasing, f prime is less than 0. Concave up, the second derivative is greater than 0, and the second derivative for concave down is less than 0. So let's do some algebra on f of x. Let's find the first two derivatives. So the first derivative will be 8x to the third minus 8x, and the 1 will drop off. The second derivative will be 24x to the second minus 8. Okay, so now we do our work. Part A, we work with the first derivative. We set the first derivative greater than 0 to find increasing. And actually what I could do is I could just find where it equals 0 and test around it. So let's do that. Let's set it equal to 0. Find out where the derivative is equal to 0. Use factoring methods here. I'm going to pull out an 8x. That would leave me with x squared minus 1. One more time. Let's factor x squared minus 1, excuse me. That gives me 3 zeros. X equals 0. X equals negative 1. X equals positive 1. Now graphically, let's look at what that would look like. Okay, I'm just going to do a horizontal axis here. Go here's x equals negative 1, positive 1, or excuse me, 0 and positive 1. Now a cubic function with a positive leading coefficient will go down to the left and up to the right. So naturally, the graph of f prime should look like this, or something like it. Not accurate on my local maxes and mins, but for positive and negative intervals it should work. So I should be able to say that f is increasing on the following interval where the derivative is positive, right? Where f prime is positive. So here's where f prime is positive. Okay, so I would go from negative 1 to 0, unioned with 1 to infinity. All right, outstanding. And decreasing on those other intervals. Clearly, whatever is not already used on the increasing intervals, because this function is not constant at any point. Okay, so negative infinity to negative 1 and 0 to 1. Okay, the other way that you can do this is you could test, right? So if I worked out and said, well, what is the value of f prime at negative 2? You would find out that it's less than 0. And then what is the value of f prime at negative 1/2? You would find out it's greater than 0. Right? So you would know that in that interval, you would have positive derivative, and then negative here in this interval, and then positive over here. So you've tested intervals before in pre-calc. You would do it again using this process. This is testing intervals or testing values between zeros, and the other method would be just taking what you know graphically and applying it. Okay, so let's look at part B. The second derivative is 24x squared minus 8. I'm going to do the exact same process and find these critical values by setting the second derivative equal to 0. That means I will have, boy, what would that be? Let's factor out an 8. So I have 3x squared minus 1. If I factor 3x squared minus 1 using the difference of squares, I'd get root 3x minus 1 and root 3 x plus 1. So the two critical values that I would get would be plus or minus 1 over root 3. Okay. All right, now I'm going to do this graphically. I'm not going to, well, actually, you know what? I'll test intervals. Okay, here are my two values, negative 1 over root 3. Then I'd have, let's go positive 1 over root 3. So I know f double prime, make sure and label, is 0 here and here. So naturally I would test f double prime at 0. And if I did that, I'd plug a 0 in here for x, I'd get a negative value, right? So less than. Now I can't always trust that on the other sides they'll just alternate and it would be positive and positive depending on the values I'd plug in. But seeing that I'm working with a quadratic function that opens upward, I'm certain that the second derivative would be greater than 0 outside of those values. Okay, so I could say that the function f, okay, f of x is concave up where the second derivative is positive. So on the interval, let's see here, from negative infinity to a negative 1 over root 3, and then from 1 over root 3 to positive infinity. That's where the second derivative would be positive. Therefore, concave up for f of x, concave down would be just on the interval from negative 1 over root 3 to 1 over root 3. All right, there you have it. That's a little review from yesterday's lesson. Let's get into the new stuff. Okay, so more with the second derivative. I wanted to talk specifically about points of inflection. In the formal definition of a point of inflection is that f of x has a point of inflection at x equals c if the second derivative is positive or doesn't exist, and f double prime changes sign through that value x equals c. So it's very similar to maxes and mins, except maxes and mins have the criteria that the derivative has to change specifically from positive to negative or negative to positive, whereas the second derivative, that doesn't matter. Now this is all just formal definition for the fact that the function f of x is just changing its concavity. So it's changing from positive or concave up to negative or concave down. So let's find the points of inflection in example 1 here. Here I've got myself a function. It's a polynomial. I would, when I see a function like this, typically my first idea is not to expand. That's going to take you a while. I would use the product rule. So t prime of x, I'm going to use the product rule. The derivative of the first function, which is x plus 1, is 1, and I leave the second function alone. Okay, plus the derivative of the second function times the first. So that would be 3x minus 3 squared times the derivative of the inside, which is just 1, times the first function, x plus 1. So there's t prime of x. Now the temptation at this point is to try to expand yet again, and I wouldn't do that either. I would just continue on with the second derivative. And then working specifically, now I have just one term here, and then I've got a product rule here. Okay, so that first term will be 3x minus 3 quantity squared. And then the product rule here, I would pull the 3 out in front, and then do the product rule of everything inside of here. Okay, so let's specifically work that. Okay, so the derivative of the first, I'm going to do the derivative of x plus 1 first, which is 1, and leave the second function x minus 3 squared alone. Okay, and then I'm going to add the derivative of the second, which is 2x minus 3 times x plus 1. So there's your product rule on that second portion. Okay. Now I'm going to distribute the 3 and combine some like terms. So let's talk about it before we do it. I've got 3x minus 3 squared. Here I'm going to have 3x minus 3 squared again. So I'm going to add those two together. That'll give me 6x minus 3 squareds. Okay, and then I'm going to distribute this 3 to that 2, giving me also 6x minus 3 times x plus 1. Okay, so ultimately my goal is to find where t double prime equals 0 and then change its sign. So I'm going to have to do a little bit of expansion here to combine some like terms. So this is when, especially when I get down to just quadratic terms as my highest power, I can work through that relatively easily. So this would be x squared minus 6x plus 9. Plus, this will be 6, foiling that out, x squared minus 2x minus 3. Now I'm going to combine some like terms in a moment here. Let's expand this a little further. That's 6x squared minus 36x plus, what is that, 54 plus 6x squared minus 12x minus 18. Okay, so t double prime, I'll be able to factor this hopefully in a minute. That'll be 12x squared minus 48x. And 54 minus 18. Oh gosh, what is that? Oh, I don't even know. That's 54 minus 20, which is 34, plus 2, which is 36. It'll be plus a 36. Okay, so as we look for where the second derivative equals 0, my advice to you is if you can, take out that leading coefficient. Here it's 12. So I'm left with x squared minus 4x plus 3. Factor that further. So that would be x minus a 3 and x minus a 1. Okay, now clearly I see that I'll get critical values at x equals 3 and x equals 1. That's where the second derivative is equal to 0. Okay, so I can again do this graphically. And I'm going to graph the second derivative of t of x. I know we're equal to 0 at x equals 1 and x equals 3. Testing values, I would clearly see that the second derivative between is 0, or excuse me, is less than 0, and the second derivative on the outsides are positive. I could also see that graphically t double prime is a quadratic that opens upward. And so I would have second derivative values that would follow as such. So each of these values, x equals 1 and x equals 3, are both points of inflection. Point of inflection at x equals 1 and 3. And the reason why is because the second derivative equals 0 at both of them and changes sign through them, right? So it doesn't matter if it changes from positive to negative or negative to positive. It just matters that they do change sign and that it's either 0 or undefined at that value. Okay, so we found the points of inflection. Let's look at another example here. It says analyze the concavity of f of x and find any points of inflection. So that what analyze the concavity means is find where it's concave up, concave down, or neither, and then find the points of inflection. So let's just do some derivative work here. F prime 3x squared minus 12x minus 12. F double prime, I'm just using f prime to get f double prime, I don't even need it, right? So that'd be 6x minus 12. This will be a nice one. Okay, so I'm just going to sketch. This would clearly equal 0 at x equals 2. Okay, so at x equals 2, the second derivative is equal to 0. A line that has a positive slope should look like this. So the second derivative would be positive on this interval and negative on this interval. Therefore, f is concave up on the interval from 2 to infinity. F is concave down from negative infinity to 2. Okay, now let's look at points of inflection. Not a whole lot of work to do here, but there is a point of inflection at x equals 2. And as we can see, the reason why is because the second derivative goes from negative to positive and equals 0 at x equals 2. Okay, some basic stuff there. Let's get on to some other things in the next slide. Okay, no math pun intended here, but this question will seem maybe a little bit extreme the first time you see it. And the reason why is because there's so many unknowns and there's a lot of theoretical business going on here. So let's analyze it with the knowledge we have at this point. So if y has local extrema at these two values, that means that f prime or y prime at those values, x1, is equal to y prime at x2, which is equal to 0. That's where we have local extrema. I mean, it could be undefined and there was a change in the sign of the derivative, but we can make an assumption that that's true. Okay, so in part A, it says, show that b squared minus 3ac, or b squared is greater than 3ac. So first what we need to do, since we know we're dealing with extrema, is we need to find the derivative. So y prime is equal to 3ax squared plus 2bx plus c. Okay, extrema are the zeros of that function. So because I don't have values for a, b, and c, I can use the quadratic formula to find the zeros of y prime. So I'm going to take and use the quadratic formula, which this is kind of confusing, but a is 3a, b is 2b, and c is c. So yeah, kind of funky, but you can do it. I know you can. Okay, so we're going to take the opposite of b over 2a plus or minus the square root b squared minus 4ac also over 2a. So let's talk about what 2a would equal. Well, a equals 3a, so 2a would be 6a. Okay, the opposite of b is going to be negative 2b. B squared is going to be 4b squared minus 4ac. Well, 4 times a is 12a times c, so I get 12ac. I'm going to write that in yellow because it's combined. All over 2a again, which is 6a. Now, only a portion of this matters to us, right? Where do you see a b squared and an ac? Yeah, you're right. Right here in what's called the discriminant. Right? So if there are two zeros, which it's telling me there's two values I know are zeros for y prime, x1 and x2. Since there are two, if you remember back to some trig, if there's two real zeros to the quadratic formula, then b squared minus 4ac is greater than 0. Okay, so what that means for us then in this part is that 4b squared minus 12ac must be greater than 0. And I'm not going to continue this color scheme, but what you'll see then is that 4b squared is greater than 12ac, and if I divide both sides by 4, I get b squared greater than 3ac. Look at that. That is some cool stuff. Okay, now let's talk about part B. It says the x-coordinate of the point of inflection is x1 plus x2 divided by 2. Okay, so this is kind of confusing, but it's doable. Whenever we're talking about point of inflection, we need the second derivative. So the second derivative would be the derivative of the first derivative, which would be 6ax plus 2b. Okay. Now, when I find the 0 of the second derivative, all right, I am setting the second derivative equal to 0, and I'm solving for x. So it looks like x would equal negative 2b over 6a. Okay, this is kind of cool. Check it out now. Right there. Okay, so now graphically, I'm going to show you how this works. All right, here are zeros, whatever this quadratic looks like. They're x1 and x2. All right, so whether this function, I don't know what a's value is, right? I don't know if it's positive or negative. But what I do know right, is that the graph of f prime looks like this. Okay, so if I were to look for a point of inflection on the graph of f prime, it would be where the slope of f prime equals 0, okay, which I would target right here. The slope of f prime is f double prime, and changes sign, right? So the slope of f prime is negative, then 0, then positive. Or potentially, let's say a were, I don't know, negative. Same thing. So, right, in this case, it does not matter because whether a is greater than 0 or less than 0. But I know that this value, whatever this is, its second derivative is equal to 0 and changes sign from either negative to positive or positive to negative. Now, the cool part about quadratics, and this is really convenient, right, is that this point, x, let's call it x3, is the midpoint of x1 and x2. So x3 is equal to x1 plus x2, x2, go figure, divided by 2. Outstanding. Okay. It's a bit more abstract than the others we've seen so far, but it's a good practice. All right, let's move on. Okay, time for a little curve sketching. This can sometimes be a challenge for those who visually are just not the best yet at identifying first derivative to second derivative or function to first derivative. But here we go. Let's do it. Given the following graphs, graph the first two derivatives. So I'm going to look at these first two graphs up top. This function that's given is f of x. I'm going to graph f prime. So the first thing that I always do is I look for where the slope of f is 0. So here and here I've identified slopes of 0. So those are going to be outputs of 0 on the derivative function. I'm estimating these values. Okay, then I analyze the slope. So a small slope, so small positive number, getting bigger. Looks like it maxes out right about here. And then the slope starts to come back to 0. So what I see on this first portion of the graph is potentially something that looks like that. Okay, likewise, I'm going to continue in the next interval. So negative slope, small negative slope, getting bigger, probably at its biggest right about here, and then it starts to come back to 0. So small negative slope hits its biggest, comes back to 0. All right. And then, again, analyzing that third interval from here, small positive slope, and then starts to increase. So the output value increases like that. There's f prime. Now I'm just going to do the same thing on f prime to get f double prime. Okay, so I identify a point where the first derivative is 0, or excuse me, the slope of the first derivative is 0, here and here. I'm going to identify those points as zeros for the second derivative. Okay, and again, I'm just estimating these x values. And I'm going to do something like this, and it looks like something like that to finish it off. There's f double prime. Okay, outstanding. Let's continue. Let's look at the next one. Again, f of x. We'll go f prime again in green. Slope of f is 0 here. Looks like 0 here. Looks like 0 here. And then analyzing, I see positive slopes from here to here. Positive slopes from here to here. So let's do that. Looks like, let's go positive slope steep, then it's closer to 0. And then in the next interval, small negative, biggest negative right in here, smaller negative coming to 0. So it looks like that'll do something like this. Then a small positive maxes out and then comes back to 0. And then negative, just like that. There's f prime of x. All right, second derivative, same thing. I identify where the first derivative slope equals 0. Okay, I'll have negative values for the slope of f, which are negative outputs for f double prime. And then follow suit likewise. Okay, so there's f double prime. Get some practice, guys. It's good for you. It'll help in the long run. Okay, let's look at this last question here. Given the graph of y prime, find each of the following. Okay, so first thing you got to know is you're looking at the first derivative. So f is increasing where the first derivative is greater than 0. So let's analyze this graph and see where the first derivative is greater than 0. Since this is the first derivative, I'm looking for positive outputs, and that's where the first derivative is equal to 0. Okay, so that's where the function is increasing. So from -4 to right here, I don't know what that is. Doesn't ever look like it goes below 0, but I want to know where it's greater than 0. So let's call that 3.5. Okay, 3.5. So I would say from -4 to 3.5, and then 3.5 to infinity. That's where the function is increasing. Now you might say, well, why not write at 3.5? Because it just stalls out and then continues. You know, I'm always careful to just, if it's not greater than 0, I don't include it. Okay? Now decreasing would be where the derivative is less than 0, and the only place I see that happening, of course, where f prime is less than 0 is from -infinity to -4. Okay, concave up, concave down. That has to do with the slope of the function that we see. So wherever the slope is positive, so concave up, I'll just draw that for up. That's where f double prime greater than 0. Let's identify that. Well, the slope of f prime is positive from -infinity to -1, and then from 3.5 to infinity. So -infinity, -1, and 3.5 to infinity. Now these typically are complements of each other. By that I mean like the two of them set up the entire real number system, but not always, okay, because we're not technically including -1 and 3.5. So it's just complements of each other in that way, okay? Identify and classify any local extrema. So this is good. Let's identify max values and min values for f. So how do we identify a minimum value for f of x? Well, that's where f prime is 0 or doesn't exist and changes from a positive to a negative. So I see f prime changing here, but it's not from a positive to a negative, it's negative to a positive. So this value will be a max value or a local maximum. Okay, this is not, right here, at x equals -1, is not a local maximum for f. It is a local maximum for f prime, which we'll see ends up being a point of inflection, okay? Here, interesting, goes from positive to 0 to positive. Well, that f prime doesn't change sign there, therefore there is no local extreme there. Okay, so there is no min value, local minimum for f of x. All right, the local max value for f of x happens at x equals -4. And that's it. Okay, so part D, identify points of inflection. Well, point of inflection happens when the second derivative or the slope of the first derivative equals 0 or doesn't exist and changes sign. So the slope of the first derivative equals 0 here and changes from a positive to 0 to a negative. So this is a point of inflection, as well as right here we get the slope of the derivative is negative 0 positive. Therefore I have points of inflection at x equals -1 and x equals 3.5. Alright, you guys, that's a little bit more with the second derivative. Hope it made sense. Shoot me a message if it didn't. We'll see you in the next video.